videos, though, we're going to talk about like basically how you can take vague questions and then translate them into actionable business outcomes using data analytics. We'll show you like how to look at the data. Maybe it might be unstructured, or it might have to be cleaned and transformed. Maybe you have to build a data pipeline to start with like the information that you have, but not in the right system. Perhaps you might have a business where your information is very siloed. I'll tell you how you can fix that problem. A picture speaks 1,000 words. I think that was Shakespeare, or someone talking about Pablo Picasso, saying that what you can capture in an image is more than you can convey in words. And it's like Sherlock Holmes, would look at the evidence and be able to make observations, and like the graphs that you have are like a magnifying glass or a microscope that allow you to inspect the detail. Sometimes you need to like just take a 10,000 foot view, look down from space and get a high level, and other times you really need to be down in the weeds. And that's the heart of what data visualization is all about. Let's talk about that, right? That's a huge opportunity. An AI that allows us to generate things like the OpenAI ChatGPT app, or using Midjourney to create images. Advantage, because I've been teaching in predictive analytics, starting a business in Texas. I've worked with some other business partners that have a lot of brand awareness. They have an MBA, they have the business savvy. And so, like, if we take our databases, our collection of education materials, we package them up into a single product that we can offer, that this can really help to transform the educational market. So, given my experience at some major companies like Expedia Group, Willis Towers Watson, the insurance brokerage firm, also the actuarial consulting firm Milliman, I got experience like learning for actuary exams, and I can bring that knowledge to the ecosystem to provide a better education experience for people everywhere, so that you can create a variety of graphs that will meet your problems. And what you don't want is like to be faced with a new problem and say, oh, I haven't heard of this type of graph. I haven't worked with a Sankey flow diagram. I just thought of a random thing. And it's like, oh, that's something I haven't seen before, so I can't do data analysis. Sorry. No, because there's really multiple ways of tackling any single problem. Let's dive into the basis between like what is structured, unstructured, or semi-structured. We all know that tabular data that we see in spreadsheet has one a variable per column that's already structured, right? If you get your data from like clickstream websites that's in like a JSON format, or it might be just an HTML or some log from a web page, that's unstructured. So how do you resolve that? Well, there's something called a data lake. I know, like a lake that you go swimming in, but this is a data lake that has a way of collecting and amassing the information from all of these sources. And like the simplest data lake example I can give is on Amazon Web Services. If you just have an S3 bucket, and then you just dump in the contents of videos and then data files, and then you have what's called an index file, which is the metadata about the information from that links back to the original videos, so that when you're navigating the data lake, you have an index. Indexes, you see a lot in programming. The concept of an index. It's a way of referencing information, and I have like a lot of examples from using articles like beautifully written Tableau dashboards and things about like, there's a chart here that I'll show that's about capital markets and all the world's money through the stock market, private equity, real estate, etc. But like, if you just look at a pie chart, for example, and you just look at the pie chart, you know that pie charts are actually bad. Yeah, because a straight line bar graph does a much better job of conveying the same information. The goals, though, of data visualization, like there's basically two. There's the left brain and the right brain. The left brain is about like exploration, and the right is like communication. You want to do speed, iteration, ability, work with many dimensions, and be able to tidy up the data when you're doing exploration. And when you're doing communication, it's almost the opposite, because you just need simplicity. You want the client to get the message, and you want like consistency in language and colors and et cetera, et cetera. Like you might just use a color palette with like a few colors, whereas when you're doing exploration, if you look at all colors of the rainbow, it gives you a better understanding of what's actually going on. There's different phases. You start with the data in a database, and then you have to run queries, you visualize it, then you fit a predictive model, and then you go back to querying and transforming again. And once you've gone through this cycle, you eventually get to a writing phase where you have to communicate it, put it into a Word format or a PDF that you deliver. There's like a lot of ways that you have to transform data. I remember the acronym ETL, extract, transform, load. You have to do things like create new features, reduce factor levels, apply log transformations or skew transforms. If you also have to create bins for numeric variables. If you're working with natural language processing, you have to like do like tokenization, encoding, and then decoding. You have to create dictionaries as ways of indexing and referring to information. That's all ETL. You have to visualize. Like when you visualize, you can look at like univariate plots or bivariate plots. That's when you're looking at like just one variable by itself, or bivariate, which is when you have an X and a Y. You have to, so those are sort of the key principles of constructing graphs, is that you have an axis, then you have different elements like the color or a point. It could just be like, you might use a triangle for one type of point and a circle for another. Those are all like what we call mapping. And so sometimes, you know, bad data viz can actually make the problem harder to explain and understand. That's just like any type of tool. It can be used for good, or it can be misused to like obscure information. Instead of making information clear to understand, you might like see it used sometimes to like make it hard to explain information. You can also like just look at tables. Tables like spreadsheets, sometimes that's like it's harder to misinterpret that data. And also just never forget to inspect the target, like the target variable, the thing that you're trying to understand. If it's like, well, we're working on improving open rates for our email. And so open rates is the target. And so we'll look at like summary statistics. What's the average open rate? What are the open rates by geography, by type of device? If it's a tablet or a computer, we'll just like really dive into the specific thing that we're looking at. Then once we get to the point where we have some model that we want to use, then you have to conduct a test where you split the data into testing and training. So then you fit and interpret the models. This is before you've gone through and like communicated everything. Then once you're satisfied with the result, you can like have to really like, I remember one time I was working with a client, and we had spent an enormous amount of time fitting a result, going through an ETL data process. It was collecting property information for Norway. We had sent out like an email outreach campaign to thousands of property owners. We collected the information, we'd assembled the information, and We had tried like different data sources. We had like done a lot of work. But somewhere along the line, when we were documenting everything, organizing it, and then communicating it, like lots of people dislike writing documentation and organizing things and just putting up metadata. That's like, you know, why we have to have data managers, but also like program managers, and we have to have like structured work environments where we're doing things on Confluence. If you're not familiar with Confluence, it's basically like a Wikipedia page of the task that you're working on. If you work a lot with R, they make it, well, I'm not going to talk about this. I was going to talk about specific packages and libraries, but the thing is, packages and libraries like change over time. There's different recipes for making like good graphs. The most simple graph you can make is a histogram, which shows the density. A histogram only shows one variable at a time. So the x-axis is the value, and the y is the frequency that it occurs. Then there's also like just a frequency polygon, or a smooth density, which artificially like makes it look like the data is like really continuous, and it makes it look better than it might be. But then you do this fancy smoothing, and it makes it look nice. But it doesn't mean that the data is really that way. When you work on histograms, you'll notice right away that the distribution is highly skewed, meaning that you have like a few values that are very high that are like moving the mean, because like a mean, an arithmetic average is heavily influenced by outliers. And so if you look at the median and then say, well, the mean is much higher or lower than the median, that's telling you that the data is skewed. If you want to like make a correction for that, you can apply a log transform. And then if you're just using like a regression model, a GLM, you can use a log link function instead of applying the log. A caveat to histograms. If you look at your histogram and you have like nice bins that are about showing a curve with a distribution, and you think you understand the shape, but then you notice there's spikes, and those spikes could just be because of the number of bins that you chose. And so if you change around the number of bins, sometimes it can manipulate the shape of the graph. You can also do things where you break up different distributions of your histogram using different categories, and these have to show like the x-axis will show the target, of course the y-axis is the density, and then like a color will show you like if that variable has high predictive power, then there will be large differences across the values. And if that means that the predictor is doing a good job of stratifying the target. On the other hand, if your graph looks like this, where the data is bunched together closely, then there's not a big difference. If the graph is jumbled up, it means that the predictive variable has low predictive power, and there's only small differences in the target across the different values of the predictor. It still could be that there's predictive power, but you have to look at other variables at the same time. Bar plots, like The x-axis will show the category again, but then the y-axis shows the number of records. It's a good idea to combine levels that have few observations into new groups. This reduces the dimension, but it increases the predictive power of those groups because they have a larger sample size. Don't combine groups if they have a big difference in the mean of the target variable. So that's the gotcha. There's if you have a box plot, it's also called a box and whisker plot. It shows the distribution of values. It gives basically the same information as a histogram, except it also shows you the minimum and the maximum value, the median, the 25th and the 75th percentiles. You can look at variations like this violin plot. It shows the, in this case, you can also, well, when you do, there's also something called an interaction, which is when the impact that one variable has on a model changes depending on the values of another variable in the model. And here you can see that there is a factor, two factors are interacting because there's differences in the median across the different categories. Like stop signal, you can see is a little bit higher for all times of day, morning or night. In this case, you don't see an interaction because the box plot shows morning and night with the same orange and yellow, or orange and blue median values across the different, across morning and night. There's no difference. Then like scatter plots. Scatter plots are, well, advantageous when there's correlation or nonlinear relationships. They're also just easy to read. The disadvantage is they get like crowded with a lot of observations and they get skewed when outliers are in the data. I've looked at plots where there's a really high number of points, and for my own work, I like to look at the graphs, and then when I'm like presenting the results to someone else, I will just look at a higher simplified chart. And it's always good to be able to refer back to the like scatter plot if you don't really, you want to get some reassurance. Like it shows correlation and relationships, even if they're non-linear. So we had to like work together in a team. It was like several analysts collecting data, validating it, had to use Python to collect information from the database. And then it was like a lot. It was a lot of points on the graph. And like when I was doing that, I would make the points transparent. I would decrease the visibility or make the points smaller so that you could see the points like individually, really kind of play around with the aesthetics, set the alpha values and so forth. And so I was able to like do that. And that helped to like really understand, helped me to really understand the problem, and then I could deliver a good result. We ended up like achieving like a 95% accuracy rate. We collected the data, we were able to deliver it on time. You know, it was a home run success. A lot of that comes down to like being able to look at different types of graphs, like a bivariate density where you look at just lines and the points of the graph show the distribution or the density of the data. You can also do like scatter plots with different color mappings, where you can look at multiple variables x and y together with a color that's as third variable, and then you look at the slope of the lines and you compare the values of the color to see if there's an interaction effect. So this allows you to take like scatter plots and make them into very effective tools. But I'm focusing on like practical examples. Like for example, predicting hospital patients, traffic accidents, claims, customer phone calls. Those are all data sets, and you have to think about private information, like in the hospital, the race and political affiliation are protected. And so if you're working with like traffic accidents, let's say you're using data from 2015 to predict accidents in 2020. What's the concern there? Well, you're using old, out-of-date information. If you hear that you're building an insurance pricing model to predict claims, you have to ask, are all the variables legal? If you're using customer phone calls, using data, like, are you working with data that can't easily be explained? If it's like a call center, they got hundreds of calls, maybe you're trying to use a text to voice to text model and then extract features from the text information. That's something that's like really complicated. So it could just be that you don't have the tools to do it. In the healthcare system, like you read about things in the newspaper. Like there was this large health insurance company in the US and they were accused of racism over their use of a predictive model. They used medical claims to predict health recovery in hospitals. They were predicting health costs, and minorities appeared sicker simply because they had less access to affordable care and thus needed to spend more on average. In an example of racism in court sentencing, a federal court used a predictive model to estimate the probability that a criminal would recommit a crime if released. They used arrest data. They were predicting drug offenses. Black people were much more likely to be searched by police than white people. Even though the model didn't contain a race variable, the result was racist. Okay, so like, once you've read the data dictionary and you've checked that the data matches the real data, and you've identified the types of variables, whether they're categorical or numeric, you've checked for missing values, and you've decided the time frames and variables that you want to use, then you set like a baseline. Well, there's different types of missingness. Missing at random, hidden missingness, and missing not at random. You don't have to memorize these things, by the way. This is really just like illustrative. How you can remove observations, first of all. You can create a new level, which says missing, and you can impute the mean. Or you could just like delete the variable altogether. If you remove observations, there might only be a few values like when they are missing at random. So that's like the cleanest, simplest approach if you get lucky. If you have more values that are missing, you probably will assume that they're missing not at random. MNAR. If you have to impute the mean, like if you don't want to remove the data, but you want to still fill in the values, let's say you're fitting a deep learning neural network, which doesn't allow for missing values, then you just put in the mean value. Let's take an example. In this case, is this missing at random or not? If you're predicting whether or not a person will pass an actuary exam, and you're looking at the variables, study hours, eats chocolate, life, if they're in the life insurance industry, if they drive to work, if they bring their own lunch. And the pass percentage for non-missing records, and then the pass percentage for missing records. So you're looking at the pass rate, not by students, but by variable. So it's like a flip, right? Most of the time when you look at a percentage, like it's like average student pass rate, but this is average pass rate for the variable study hours being present versus the pass rate when we don't know what the study hours are. So like, how can you approach this? How can you fix this? Like, here's a simple quiz. You could do MNAR. Well, I'll just show this on the screen, and you can make a choice like connect the dots. And the answer is you can always fix the variable just by like, well, no, the only time you should remove all the observations is when you're sure that it's completely missing at random. If you have like some type of hitting missingness, there isn't really much you can do. Well, you might just have to do all three, where you create new category for other, and then you remove the variable altogether. If you're missing not at random, you don't want to just delete the records. You want to like either try to fix it by creating a new category, or just or don't use that variable altogether, but don't remove observations. There's a lot of math. Feature engineering is the process of finding ways of adding predictive power by doing addition, subtraction, multiplication of the variables. And that's when you call them features. Like a feature, think of like a feature. Like if you're looking at a painting, and it's just to say this is a painting of people at a concert, right? Imagine a picture, people at a concert. There's different features like people, or lights and stage, or the colors. Those are all features. And what a deep learning model does when it looks at an image is it can extract those features, and then it can compare those features with other pictures. And like, that's how they work. Like you can look at so like if you're looking at like the difference, it's just like, or you can also look across other mathematical measures like the logarithmic scale, or you could create polynomials of or powers or ratios. You can take the ratio of x1 to x2, or you can take the square root or like really complex manipulations. That's where like algorithms can really come in and add tremendous predictive power. That's the advantage of using transformer or neural network based architecture, because it automatically creates the features for you, and you don't have to, like, if you're in a linear model or a tree based model, then you can't, you have to do that feature engineering. Actually, no, scratch that. If you're on a tree based model, like a boosted decision tree, an extra trees, a gradient boosted trees, it actually does the feature engineering just like inherently, automatically. But if you're using just a linear model, it doesn't. If you're using a neural network, a feed-forward neural network, a concurrent neural network, a transformer, encoder, decoder, it automatically does the feature engineering by the process of once it fits the weights and it has the multiple layers that captures the information that you get from feature engineering inside the prediction. When you do like summary statistics, sometimes it's a lot easier to just think simply. Like the mean measures the overall behavior. The median is the center or the most common. The max is the highest outliers. The min is the lowest outliers. The variance, spread of values, and the percentage is just the overall behavior. So like in this example, I look at the summary and I see that the days has a high maximum value of 14, and there's a high number of, there's 3 cases that are unknown gender, and the age is, I look at the category other. Well, this is where I get stuck in what's called analysis paralysis. So I try to also look at the graph. I look at the histogram and I see the overall behavior. I can sort of guesstimate that the mean is about 4, and then I can just say there are 3 missing values. I just removed these because there are not enough value to make a difference. The target variable is the number of days that a patient spends in the hospital after being admitted. This has a mean of 4.4 and a median of 4, indicating that it is right skewed, which is also set from the histogram below. And I would do this on Microsoft Word. I would then do the sort of descriptive stuff like in Python, Pandas, or not Python, in a Jupyter notebook or in RStudio. So, like the best graphs are easy to read. And what the y, like let's look at this graph, okay? The y-axis is just like unlabeled, that says density. And then the x is like, what is this translated to into English? Like density? What is a density? Can you explain that to me in English? If you instead look at a bar where there are bars that separate out the values, and then there's labels on the y-axis to say the number of hospital readmissions, then in English you could say there are just over 2,000 hospitals which have between 20 and 30 readmissions. This combines the tabular info from a table with the visual power of a graph. In ggplot, if you're using R, you use these elements like geom, histogram, the scales, and that maps the x-axis label. And then like, yeah. Graphs should be unambiguous. That means that there's really, like, there shouldn't be room for multiple interpretation. It shouldn't be like, I'm looking at this graph, how do you think it makes you feel? You know, like I'm looking at a painting of Picasso, I'm like, oh, this makes me feel triumphant. Like, no, like, this makes me feel sad. No, like, it should be very logical because, like, I'm going to show you a classic blunder, which is when you have a mixture of bars and lines on the same graph. Which of these axes is expected and which is predicted? You see on the left, it says actual, but you don't know if that's related to the blue or to the orange. A step in the right direction is to just look at a XY graph. You can see that the expected readmissions are on the Y-axis, the actual are on the X, and like you see Massachusetts there is furthest from the line. When you looked at this graph, Massachusetts there, it's not really obvious. You can also look at a bar where you have that each state has its own bar, and it's the ratio of actual divided by predicted. And what's nice about ratios is if the ratio is 1, it means the numerator is the same as the denominator. Yeah, there's like the code that you'd use to do it in ggplot. And yeah, like ggplot is nice because you can do everything all at once. You can do the filtering, the graphing, you can add the labels, add the theme, change the color, everything just all in one code piece. When you are looking at graphs, like I mentioned, it is good to look at different colors, and there's this thing called a color wheel, which is a way to helpfully manage which colors are complementary. If the colors are opposite on the color wheel, it means that they are like complementary. So if you have like four things in a graph, you need 4 colors. You just look at a color wheel and go make an X, and then there's the colors. Like some example, like you all know what bad coloring looks like, where if you use like a pink, a turquoise, a brown, and a gray, ew, there's not really an aesthetic quality to that. Look at a company's website and find out what their colors are, and then try to use those in your dataviz. Just remember that you can be persuasive when using data visualization. There's a couple different... Realize that you can't win an argument. Let the other person see and arrive at the conclusion. And be careful to use the same language that the other person is familiar with. Be friendly. Smile. Help them to say yes and just like agree with you. Those are some of the topics. Like I talked about, what do you do as a data analyst today to provide more value? If you're doing more things that are like data engineering, or you're creating a database, and maybe you're doing more software development where you're writing the back-end code to do this, it's still somewhat useful to be familiar with this. When I'm constructing a database, I actually like to peek at the data, just to get an idea of what it is I'm working with. Because like the common example is like when you have to name variables and you're like naming x1, var1, var2, like it gets really like bland. But if you like understand what it is that you're working on, it makes it a lot easier to come up with names. And the data scientists will really appreciate that little bit of thought that goes into it. Like, you can tell like when a graph is made by an AI, and you can tell when the graph is misinformation, because if you like compare the table and the graph, you like, whoa, they just put this into ChatGPT. Like, this is just some template they got from Power BI on Google search. Like, it's not customized. And then you ask them like, hey, can you change this graph? Can you make this a bar plot instead of a pie chart? And they won't be able to do it. Like, maybe that's just because they just use a template and it's like, or the data is concealing something. That it's always like interesting, like to be able to look at the data analysis and to really be able to do the work. So thanks for watching. If you like this video, please subscribe. If you have any questions, leave a comment. And we just launched our new website, and you can actually sign up there. If you go to futuroinsight.com and click sign up on the top, you can go ahead and log in with any of your social accounts, and we're going to be able to provide benefits and an insider's version of the course on there. Yeah, thanks for watching.